Hello students, so in this lecture we shall continue our discussions on colloids. So if you look my lecture number 37, I'm giving you the basic introduction of colloids, and we had discussed about the different resistance, different rules like Hardy-Schulz rule, static stabilization associated with colloids, and we have discussed the factors that induce the coagulation and flocculation. Now, in this lecture, we shall further go into the details of colloids. So, it's colloid lecture 2. So, let's take some examples of colloids in normal daily life. So, in colloids, as you know, there is a continuous phase, there is a continuous medium, and this medium can be solid, liquid, and gas, and there is a dispersed phase. It can also be solid, liquid, and gas. So if it is so let's say if the continuous phase is solid and the dispersed phase is also solid, then they can be simple solid dispersions. They can be composites. They can be photochromatic classes. They can be fillers and pigments. So this is where both the continuous and the dispersed phase are solid. Now, if the dispersed phase is a liquid, whereas the continuous phase is a solid, if it is a liquid, then what are the different types of colloids that we can have? They are called solid emulsions. They can be butter and margarine. And then this can be an opal, which is a gemstone consisting of quartz-like formation of hydrated silica. So these are the examples of liquid phase dispersed in a continuous medium, colloids. Lastly, if it is a gaseous phase dispersed on a solid, it is gaseous phase, then the possible colloids are foams and expanded plastics. Like polyurethane foams. These are gaseous part and solid as a continuous medium. In a similar way, with the continuous phase is a liquid, and we will have solid as a dispersed phase. Then it can be called suspensions, like hydrosols and organosols. It can be a muddy water. It can be a fountain pen ink. So examples of a solid phase dispersed in a liquid phase. If both of them are liquid, this is also say is a liquid. Then the colloids are called oil water. And or water to oil, whatever. It can be milk. Mayonnaise, cosmetic creams, so and the dispersed phase is a gaseous one. Then we can have again foams and whipped cream. And lastly, if the continuous phase itself is gas and dispersed phase is solid, then we're talking about smoke, and this is the only thing. Otherwise, it can be a liquid. If it is a liquid, then it can be a fog, or this can be cosmetics. Or ink used in inkjet printers also sometimes can be liquid on a gaseous phase. So this is it. There is no gas. So this possibility is not there. Both of them cannot be gaseous phase. So these are all possible colloids that we possible in based on the different types of states of matter. Now, if we look into the size of the colloid size, you will see that it is small enough and is influenced by thermal fluctuations, not dominated by gravity. The size should be small enough to be influenced by thermal fluctuations. They are influenced by thermal fluctuations, but at the same time, not dominated by gravity. And they should be big enough to be treated as one body with average, to be treated as one body with an average density of 10 to, let's call it as 5 average, not 5 average. 10 to 10,000 nanometer per centimeter square. Oh, sorry. This is not the density. This is basically the size. So the size can range between 10 nanometers to 10,000 nanometers, depending upon what kind of colloids you are using. Now, when these particles are in the colloid system, there are different forces that act on them. Forces act on the individual particles. In a suspension, like it can be a gravity, it can be something called a drag force. Let's call it a drag. It can be due to thermal motions. So there are different types of forces we'll discuss one by one. So first start with gravity. Now suppose we have a vessel. There are two mediums. One is the continuous medium has a density rho, and this first phase has a density rho 2. Then the force to gravity is equal to mass into gravity, and it is equal to 4 pi a cube by 3 into delta rho is rho 2 minus rho 1, the difference between these two densities. If delta rho is greater than 0, that means the dispersed phase is having a higher density than the continuous phase, then this will cause sedimentation. Whereas if it is the opposite, that means delta rho is less than 0, then it will lead to formation of something called creaming will take place. So this is the gravitational force. The next force, so this is take this number 1. The next force that acts on the fluidal particles is the drag. And basically we are talking about the viscous force. So you know the formula that viscous force F is equal to 6 by eta, which is the viscosity, into AV. A is the particle size and V is the velocity with which it is moving. So there is a terminal velocity associated with this viscosity, and it is equal to 2a square. The size of the particle is a, and delta rho into g divided by 9 eta. This is terminal velocity. So this is the second type of velocity. The third velocity is due to thermal motion. So this is due to thermal fluctuations. So we'll call it a thermal motion of atoms. Or molecules in the liquid. So there will be an average force F acting on it, and that force is equal to 0. So basically we're talking about the random walk that we have discussed previously. And there is it is because the particle travels in zigzag fashion, so the average force acting on it will be 0, net average. There will be forces acting on every sides, and this is what happens in Brownian motion. Here, the forces are acting from all sides. So the net force is therefore equal to 0. The net distance traveled also is equal to 0, where r is the displacement vector. Now, wherever a particle moves through a medium, it moves through the process of diffusion. And there is a diffusion constant associated with this movement, and this diffusion constant is given by Stokes-Einstein's formula. And it is dSE, and it is equal to Boltzmann constant dVt divided by 6 pi eta A, where A is the particle size of the particle radius and this is the viscosity. So we see that there are three types of forces. First is the gravity, second is the drag, and third is the ground motion. Now we have considered individual particles. Now there are other particles in the system, not only a single particle. So that's why we need to consider many particle interaction. So initially we were considering that if this is the continuous phase, there is only one particle, but actually this is not the real case. In the realistic case, there are a large number of particles and they will interact among each other. Now, many particle interaction is given by, or explained by van der Waals. And he considered them to be attractive. The interaction between two particles, say this is one particle and this is another particle, and they are separated by a distance h. This one has got a radius r, and so interaction will be given as V is a function of h, potential, and it is equal to minus A into R divided by 12h, where we have considered here that the value of h is much less than R. That means the particles are very close together, and this value A is known as Hammocker's constant, and its value will depend upon the medium in which the colloid is placed. Like, for example, if we are talking about polystyrene, then it has got a radius of about, say, 100 nanometers. So it is in water. So if it is the distance between the polystyrene molecules, if they are, say, if they are 1 nanometer apart, then the potential will be around 20 kT, which is approximately 10 to the power minus 20 joules. And if they are, say, 10 nanometers apart, automatically it will be 2 kT. And which is 1/10 of this value. Now, apart from this van der Waals interaction, there are electrostatic interaction as well, which is considered to be repulsive. So we have van der Waals interaction, let's call it as VW, which is attractive, and we electrostatic interaction, which is repulsive. So these interactions will compete among each other. Now the electrostatic interaction, try to understand its source. Now the surface of the colloidal particle, they are often charged. Alright, so if we have a surface like this, they can be positively charged or negatively charged, and this charge is often, they are structural in origin. They can be structural in origin, or that can be associated with a surface group, a chemical group on the surface, or they can be as a result of some selective adsorption on the surface caused by the outer surface of the particle. Now, to maintain the charge neutrality, there is something called a screening effect taking place on the surface. So, suppose your particle is immersed in the medium and there are negative charges. So what the particle will do, all the positive charges inside the particle will come to the surface, or at least close to the surface. Sorry, these are the positive charges, not negative. So this will cause a repulsion between the incoming charges, that is in the medium, and there is a screening effect will take place, and the counter ions, and so the charge neutrality is preserved by a layer of counter ions. We're talking about this layer of counter ions. So the plot, we want to show it graphically. So these are the counter ions on the y-axis, and this is the distance. So formation of the curve looks something like this. So at the top they are represented by positive ions, whereas at the bottom represented by negative ions. So these are tightly bound, and the layer formation that takes place, that is called a stern layer. And the screening length is called Debye. Screening length. This is this length. This is the length at which this screening effect will take place. This is the Debye screening length, and this is again equal to, represented by K inverse it is equal to epsilon naught kBT divided by 2e square N O Z square to the power 1 by 2, where NO is ionic concentration in the medium, and ZE is, of course, is the ionic charge. Z is ionic charge. Now, if this value of H is much much greater than 1 by K, 1 by, then the electrostatic interaction, the wave vector K stands for 2 pi by lambda. Electrostatic interaction, it tends to 0. So if we represent the direction in terms of the wave function psi x, and it is equal to psi 0 exponential minus kx. So plot it, the direction will die out. So this is not value of psi, this is psi naught. This is the point where potential is psi 0 by E. So the conclusion or the inference that we can draw is, although the electrostatic interaction is repulsive in nature, but it can be screened. This is number one. And the stability of whether electrostatic interaction will be screened or not, that will depend upon the salt interaction, salt concentration. Salt concentration, or by salt concentration, what we mean is the ionic concentration in the medium, that if it has a very large part in the electrostatic interaction.